Okay? So I've met, like, in the last year, one of the most amazing guys I met, Danko Nikolic. Maybe you didn't heard about him, but I think that this talk you're going to listen here is going to be one of the things that maybe will change the whole course of data science and AI, especially as an industry itself. Danko is working on something that is truly transformational. We have been talking about the large language model, and the biggest issue is we are talking about 3 to 900 trillion parameters. That's not how the brain works. That's not how the nature works. As a physician, I can tell you that the nature is the simplest form of simplicity, the purest form of simplicity. Beside that, Danko is a neuroscientist who is developing something that's called guided transfer learning. He's not going to talk a little bit about that, but what I want to tell about this as an introduction to this is that if he managed to do so, he will solve the problem of complexity of building neural networks and large language model. And this also may be a pressure to put on, but I truly do believe that he's going to build this in the end, and he's going to be written in almanac of the AI. So without further ado, I would like to ask kindly Danko to join us on the stage as the final keynote of the first data science talk. Thank you so much, Danko.
What to say about this introduction? I've never been introduced in such a high level, so I feel really, I don't know, humbled. Anyway, what he said I was doing, I'm actually doing it. It's my normal job. I'm developing normal AI like everyone else using existing technologies. We are developing call response system where you call an AI to help you with your computer, and this AI is trying to find a solution. However, in my free time, and because I have been a neuroscientist for many years, with a focus on understanding the brain, how the brain reaches intelligence, I'm developing concepts on how to improve AI, how to improve AI technology and make a new generation of AI technology. This is not working as usual. Do we have the other one then? The other remote. Oh, here. Just move.
You will not be there.
Uh-oh. What do we have here? Nothing happened. Ah, yeah. Could I ask you next slide?
This is a good picture.
That's a good picture. So that's the goal of AI, my goal. As a kid, I wanted to have a robot at home that would clean my room. And the challenge here is, are we ever going to have robots like that? For persons like you go to a tech store, where you buy on TVs and so on, such robots sitting like this, and you pick, that one. And it can do cleaning, it can do cooking, it can do watering plants, everything around the house. And it's affordable. Let's say it costs as a new car, as much as a new car probably many people would love to have it at home, would buy it. Now the question is, what kind of AI technology we need to achieve this kind of robot? And whether the technologies today can achieve this level of robot, whether it's not. And that's what my talk about is today. Let's see if this works. Next slide, please. Take this one, third one. Okay, so I'll make one point that's going to disagree with what you just said. So there's some disagreements in the conference. I think that large language models have done everything they could, or we have done with large language models everything we could so far. Now we have pushed them to the very high level. There's not much higher we can go, because we have pretty much used the size that's as big as we can afford to build, as much energy we can use. And also, we use pretty much all the data we have to train them, so there's not much up. Right? And it's not only just my words. Actually, the founder of OpenAI said exactly the same thing. So we need new technologies for further advancements of AI. Of course, now that we have GPT technology, there will be lots of applications development. For many years, it will be exciting, and lots of new cool things will come up, new products, it will be amazing. But if you want to bring AI to the next level, we need new technology. And the reason is the scaling issue, right? If we plot here down the intelligence of our AI and the resources that we need, like for example the number of parameters, it explodes. And also the same curve you get for amount of data you need for training, and the same curve you get for the amount of energy they burn. Right? It's not sustainable. It's simply not sustainable, this deep learning technology. Right? So you have to start, and we are maybe, is that later? Yeah, I look really small. My finger is bigger. So, if this is GPT-3, this is GPT-4, right? And GPT-5, if it ever will be right there, up there, right? On the ceiling or something like that, right? To make a really big difference in comparison to GPT-4. And we don't, it's just, you have to stop at some point. It just doesn't go anymore. Now, in contrast, human mind doesn't scale so bad. So we actually learn pretty much with a linear curve, right? To double our intelligence, we don't need 100 times more data. We just need twice as much data. We learn a new fact. It takes approximately as much time as it took to learn the previous fact. Not for deep learning. If you add a new fact, you have to relearn the whole thing. And you add a new piece of information, you have to relearn the whole thing. Plus you need more parameters to put it in. So big difference in learning. And even bigger difference in application of knowledge. Flight application. If I learn some new piece of information, I can apply it so many new different ways without having seen these examples. I can just infer it. Deep learning has hard time to do that. Even ChatGPT, or GPT in general. They need to see all these examples. That's why they need so much data, right? The amount of text that GPT sees is equivalent to million people over 1,000 years what they experience. Right? And now I'm going to give an example how powerful human mind is. Right? So let's say I will give you now, I will have you learn something very quickly. I tell you, this is a car. I think you can accept it. You learned the fact. Now let's see whether you can apply, generalize this knowledge. What is this then? If that was a car, what's that? Try, yeah, look. No deep learning model can do that you did it without any new examples. And what's that? A train. And now, amazing, deep learning cannot do that. Now let's go back, and I'm going to retrain your minds now. This is not a car anymore. Now this is a table with two chairs. So what's that? It's tables, maybe a restaurant, something. What's that? 3 tables, a classroom maybe. Jury. So you see how flexibility is. We learn a new fact we can apply it to so many different situations immediately without having to see all these millions of examples like deep learning has. And so we have linear learning and flat line of application within a certain domain. So we need the next generation of AI, new technologies more similar to biological brains that can do actually things like that. And I'm going to tell you how I think this is going to work. What are we going to need to do? And to understand it, I have these few slides. So this is the classical paradigm. We have a network that produces cognition, that thinks, that makes decisions, that does all the calculations. You know all that. Plus we have a learning mechanism that trains the network, sets up the weights. Right? Everybody knows that. So basically we have 2 big sets of algorithms. We have algorithm of the network and the algorithm of the trainer. Now what we need to do to reach this level of intelligence, we have to put these 2 apart, the network and the learning, and add a new set of mechanisms. We are not having them yet, but we need to add them. And they're relatively simple, and I explain to you what they look like. Let's call them gates. I like to call them gates. The third box. We have so far two toolboxes with algorithms. Now we need the third box that will sit in between those. If you want to learn the background theory, you can look at this paper here. Now, what do these gates do? So let's look at the left side. This is the classical way how all the deep learning networks work. You have input, you have weight, multiply input by weight, you sum it up, you have some transfer function, you produce outputs, right? And you have many of those. And you set up these weights and you get your network big intelligent. This is all good. We need all that, plus we need to add something that's called gates. Gates that open and close wires. So here you see the black one is closed, so things can pass through. This one is open, this one is open, this one is open, and so on, right? So you basically, these gates select a subset of a network for function. But these gates are smart. So how do these gates work? What do they do? Why are they so special? They have only a few small properties, but very, very useful properties. They're smart in a sense that they're looking what's going on around. They also learn, they have to learn, and they know when to open and close. So far so good, but it looks like it's just another neuron. But they have one more property that you don't see here. They stay open for a longer period of time. So now non-cognition, like they could stay for a minute. That's what happens in our brain. Like, as you think something, there's some gates open and closing. And the opening and closing and staying there for some half a minute, depends for a while. And then spontaneously they just go down. They keep changing the network as things are evolving, as the world is evolving in front of us. In the brain, we have actual mechanisms, molecules that do that, that have names that are tongue twisters. If you're not a neuroscientist, sometimes neuroscientists use like really complicated names. You can't even talk about these things. Metabotropic reception, G-protein-gated ion channels, that's things we have to use. So I published this year a paper describing how these molecules relate to this gating problem. Now, the next question is, and that's a really hard one, that's probably something I cannot answer for you, and what you would like to know. You would like to have, everyone would like to have intuition. How does it work? How does it bring something better? And that's a really hard one to answer. It's not really simple. I cannot do it in a short talk. I don't understand everything myself, but I have made, I think, a lot of progress. And I'll give you some idea here, but only very, very little from what you need. So what I'm asking you, sort of to trust me that this should work. Give it a chance. It takes time to understand how it works, why it's beneficial. But I'll give you some idea now. Right? So the classical paradigm has input-output network, right? Everybody knows that. And very important thing is that the result of a cognition is the output. Right? And the output is also what the network does. If the output is like the category that has been decided as the output of cognition. If this neuron is connected to moving a robotic arm, then it's an action. Both action and cognition, they're all outputs from the network. But here, with the gates, not anymore. These things are separate. The output of the network is the action, what the robot does, cleaning, vacuuming, moving, like this. But the thinking is the gates, exclusively the gates. Right? So you have basically two separate worlds that are connected, but two separate worlds, two separate mechanisms. If you introspect yourself, you will notice that your thoughts and your actions are sometimes disconnected. You walk and do this and you're thinking about something else. You can do that. The reason, classically, why we think we are able to do that with this theory is that because we have different networks. But in fact, what I'm saying, you could do it in the same network, but you have these gates inside. that open, smart gates that are trained, that open and close, and they do the thinking. And rewiring the network while thinking, and by rewiring the network, determining how you will produce output, and therefore determining how you will behave, what you will do. Yeah, what we say and do, what we think. Okay? Gates are smart. They need to be trained, much like weights are being trained. And so you cannot just throw some gates on it. You have to actually find a way to put them all together, to tune them up, to make the network intelligent for these gates. So that's going to be a hard problem. The next difference, or the next part of intuition on how this may work. This is, again, the classical paradigm we have in the brain, we say layers, or in machine learning technology, we say layers in the brain, in the neuroscience, we say brain areas, but basically we have stages. We have input, then processing here, produces our output, now becomes input. For this layer, then the output from this layer becomes input from the next layer, and so on. That's why deep learning is called deep, because it has many layers. Right? Now, what we do in the new paradigm, we don't have anymore this structure. These different areas or different layers are not anymore different. They're all working parallel. Everything's working parallel. You get this sequential change by iterating. So you run your input through the entire network once, and you change the gates change states. So the network is running in your state. You run the input again. Now, the next time the input will pass different ways because the gates have done their job in rewiring the network. But again, the second time, due to different passage of inputs, the gates will change again in a new way. So instead of having here the first area detecting raw features and more complex features, you will have iterations. First run, you change the gates for simple features. Second run, a little more complex features. Third run, you realize, that's my grandmother. I recognize the person, I made a decision. And you can iterate like that. The nice thing here is that you don't have a fixed number of stages. Sometimes if it's a simple problem, you do one or two. If it's a complex problem, you can spend 5 years moving over and still not finding a solution. You can do it as long as you want. Here's the paper that describes partly how this works. I don't have a full, complete explanation yet written. I'm writing the book. When it's going to be finished, I don't know. I don't want to make any promises because I have already broken them multiple times. But there is something that you can get a taste of. There's the architecture that I was talking about. We have that one more thing here. And we all know that the network has to be trained. Staying here, the weights connections have to be trained. But also, I've told you that the gates need to be trained, right? That's a new thing to training, and we have to figure out ways how to do it. But also the learning mechanisms will need to be trained. So the learning mechanisms that we have today are quite general. They're generally quite general. They can learn almost anything. But if you can learn almost anything, it means that everything's hard to learn. One way of accelerating learning is to be targeted, to know what you're looking for. In machine learning, we call it inductive biases, right? And you can learn the learning, and there has been some research of course, in machine learning to learn the learning. And by using this theory, this entire theory on which I base these gates, I also developed with friends of mine, taking this out. This is too hard, so we took this out. But we said, what can we do to take this theory, create the simplest possible learning tool to learn mechanism, training the learning mechanism, so that we can train actually deep learning networks. So the whole thing is like much, much bigger if you want to build it. But as a first step, we just said, okay, let's train learning mechanisms using this theory so that we can learn classical deep learning networks, such that we have something going on quickly. And we will need it later when once we introduce this, we will need learning mechanisms anyway. So we simplified everything like the simplest possible step. And it took us 6-7 years to get it done and working. And now we have it done and working, and you can take this paper, read this paper from Arya, if you like, and we actually put the code and equations, and you can use it already today, if you like. Right? But it's still far away from, there's no gates, it's far away from what I'm promising from the future technology, far away from the robot who can clean, but it's going to give you some taste of what I'm working on. And it may be actually useful for your own deep learning projects. And so thank you very much.
I just calculated there is more than 70 people right now in the room. So basically I just want, and it's 7 o'clock, and I think that this applause is just saying how amazing I think that person who are passionate about technology thinks about what you're doing, and it's kind of small play not to be like Martin. So the fire that to try to finish what you have started. I truly do believe, personally, I just want to say, to take a moment and to try to believe this is the first, I think, step toward artificial general intelligence, because I was thinking what you're saying, and I have tens of questions, but I'm not like taking you to take power of this position. Like first to ask, does anybody has a question? Be free to ask. Okay.
Well, thank you for your talk. I'm Danko, and you said in the end that you didn't manage yet to actually implement the gates. Is that due to just the difficulty of implementing it, or do you believe that there is some hardware issues we still need to solve to be able to make the gates?
No, at the beginning it was a question of conceptually how to do it, how to approach it. So it required lots of time just to work it out. And I have worked it out now. And now it's the question of just finding time and resources. Hardware-wise, I don't think there is a problem. We can use GPUs for that. Maybe they're not 100% optimal for this problem. Maybe at some point when we want to reach like really high levels of human intelligence, then it will start to be problematic and one would need better hardware. But for a beginning, it's fine enough. We don't need some special hardware. Not at the beginning. Still, we didn't work out how to optimally implement these gates in PyTorch, such that you get full parallelization, and then basically that you just handle tensors so that you get maximum parallelization. But it's a question for later. It's not a critical question. A critical question is conceptual problems, and it would at time and resources, team, money, all the normal stuff, I would say.
Okay, thank you so much. We have more questions.
Yeah, thank you for the great talk. One question.
Just
you are
My name is Wasit Masood. I've been working in the field of machine learning since 10 almost. My question is that you were giving the examples that we quickly learn, right? By seeing different pictures. But it is conditioned that we already know those pictures. So it's like we already, from the childhood, we have gained a lot of knowledge. Because if you say that there were tables, we know what a table is. That's why we say it's a table. We say that it's a truck because we know what a truck is. So basically it is already conditioned that we have already this knowledge. That's why we come to the conclusion that it could be multiple possibilities. So this is the question regarding, you said that the data, we don't need to know everything. So this is the question, how would you answer that? But classically, if I look at, also that's the title of your paper, this is basically transfer learning already, right? So this concept of transfer learning, it is kind of in theory already there. So I'm just struggling with like, the novelty is the guided part of it?
The what?
The novelty in your approach, is this the guided part of it? Or is this something I miss over there? Thank you.
The guiding part is the novelty that's most straightforwardly different than what you see typically in technology. But I need to comment to your saying that you already know that this is where we are here, that this is a car. Right? Now, my full talk on this topic goes, I show a child that has seen the car for the first time, and then has seen this drawing for the first time. And then for the first time, a 3-year-old child, 4-year-old child wouldn't be able to tell this is a car unless you say this is a car. But once you say the car, it accepts that this is a car. Then you go here, and then the child can generalize. If it has played with a truck, it will recognize a truck. The point is that the child has seen only this one example, only this one point, this one place, sees it for the first time, and can immediately transfer to this and to that, without having seen maybe ever drawings of anything similar or any drawings whatsoever, right? And that's where a fundamental difference to deep learning is. You can, of course, train deep learning to recognize this as a truck, and also to generalize to some level to new objects. But it has to see many thousands of other drawings of something else in order to be able to generalize. You cannot just see it for the first time ever and generalize immediately from one simple example. That was my point. I hope this makes sense. And I think you had the third point, and I forgot it.
No, there were two questions on it, but I would still argue that if I had not seen a car, how would I know it's a car?
If you haven't seen
If I
it,
have not seen a car, how would I know it's a car? So this is directed.
So yeah,
Back that
so presumption is that you have seen a real car, experienced a real car, developed a concept of a car, like real concept, and then you use this concept to apply it to this drawing and say, okay, a car has to have some place to put stuff, people preferably, so maybe that would be this. Has to have some wheels, maybe that would be this. Okay, it's a car. But only our minds can do that for the first time.
Thank you.
Okay.
Maybe can I ask one more question? I'm Mario from Contargo. My question was, the gate you're introduced, the gates functionality, somehow reminds me to the attention layers which are currently implemented in most large language models. And they kind of, I think, have the same functionality.
Yeah,
or
there is
could you
some-
maybe differentiate between those, or what's the novel approach or the difference between the gates and those attention layers? Thank you.
If I knew you were going to ask this question, I would refresh my knowledge of the attention layers. Then I could answer this more precisely. Or maybe you can use this drawing. But the point is that what the gate does in this case, it changes the neural network such that it prepares it for the next several rounds of inputs. Okay? So in a simple neural network, you have one input, you get the output. Let's say you need to recognize you have a bunch of images, you are doing your performance test, how well the network
distinguishes between, say, cars and flowers. You have just images and cars and flowers, you want to set the phone. So you randomly send car, flower, flower, car, flower, and you get out. Now, after each car, you kind of reset the network. Just everything goes to zero, and you put flower, and then comes out flower. Then not the flower, flower, car. Now, what happens with gates, it's not possible to, the network never resets. Whatever you do it stays there for a while. It's exactly happens to our mind, right? To our brains as well. So it stays there for a while, and it's basically just making a change for the next input, which is making the change for the next input, which is making, and this just keeps going. It never ever resets to anything, because the gates go back to their initial state after, let's say, a minute or something. Not that they get switched on by the stimulus. They are smart to get switched on, but the duration is no more, there's no more effect of inputs on the duration. They just stay there for some prefixed period of time and just come back, spontaneous. So, and you have lots of gates, they have different durations, and you have constant flow of information. So your network is constantly changing, never the same, never going back to some reset state. Maybe if you just close everything for half an hour, like having a nap or closing your eyes, then you're kind of getting in the reset. But still not completely, because there's internal stuff going on again. So that's a big difference from any neural network architecture, where you are not really, you don't care only about input, but what is important is that the wiring of the network that reflects the last several minutes of inputs, right? And this change keeps going. And if you train that, so here's a big claim. If you train to do this really well and be efficient in that, in using this capability efficiently to understand how language flows in, like as I speak, changes make, and at the end you understand something. Eventually, from that emerges consciousness, like what we really experience is our human consciousness, from this dynamics. So that's where the difference is, right? I hope, or does it help you on...
It's very inspiring, so thank you for the explanation.
Thank you.
And I have many, many more questions, but maybe we find time later.
Okay, you have additional question? I have also one question regarding this.
Yes, you go ahead.
All right, I thought he wanted to go. Hello, I'm Ryan, I'm a student, and I'm not an expert in that field, and maybe I got that wrong, but isn't the reality in our brains that doesn't work like that, but that rarely used neurons are being deleted over time and new ones created? That's what I remember from neuroscience. And did you think about something like that instead of the gates or in addition?
What you're talking about is a much, much slower process. Like here, I was talking about minutes. And what you're talking about is maybe months. Okay? These are two different worlds, two different universes. So you cannot, like, if you have a new thought, my claim is you rewire things. You don't create new neurons and kill other neurons. It's not biologically not possible so quickly to kill neurons or rebuild neurons. It's a very slow process. They have to first grow, then they have to move, travel, then they have to connect, grow their connection. This takes months. And so it's a different story.
But we would have the power to do that faster with computers because they're not humans.
Yeah, we could. But the brain, what I'm saying is that our brains are not, that's not what our brains are doing. And what I'm doing here, I'm trying to copy the brain. But of course, I mean, that's a creative idea, and probably you could test it and see what you get out of it.
Yeah, the question was just if you thought about that.
No, I did because I knew as a neuroscientist that it's not how the brain works. So I kind of didn't visit that space.
Okay.
There are
thanks.
more, 1, 2, 3.
We have like 4 more questions. This is the first one, the second, the third. I'll give you. Just I'm looking who is the first one.
Thank you, it was very inspiring. My name is Roman. I'm currently a student at TUWIN data science program. Though my question is, as far as I understand, this is the feed-forward architecture. And our brains are definitely not feed-forward. They're like highly recurrent, and one layers they refer in other layers, and to what extent some of our lobes are connected is also varies. And I mean, in terms of the beauty and the complexity of the biological mechanism that we have in our heads, the brain, it's the product of millions of years of evolution, and it's super energy efficient. So like chemically, it's just and the whole process of building neurons and propagating the signal around the brain, and how like the process of thinking is implemented in our brains. I would say, it's a nice metaphor, and I'm just trying to understand like what kind of cognition mechanism you're trying to replicate with the Gates approach. So if you were to bring maybe some metaphor from neuroscience and like of our how our brains work, so what are you trying to reproduce with the Gates mechanism? I hope my question was clear.
It's actually not clear. So I have a sub-question. So can you give an example of, you asked which kind of mechanisms or which kind of
cognition mechanism?
Yeah, so give me examples of what do you mean by it?
I mean, I'm not the...
What would be cognition mechanism for you?
I mean, I'm not a neuroscientist, but like if we have the neural network that needs to solve some particular task, so there are several, like for instance with LSTMs, there is some memory, so there are like blocks of memory. So that is why we're like trying to replicate this memory effect within the block. With this kind of...
Okay, yeah, good. Okay, now let's see what you're asking. So your question is, would require, like it's really a long story to answer this question, because there's so many sub-questions, so many sub-things that I have to kind of, would need to talk you through for you to get what I'm trying to achieve. But I'll try to give you a very simplified version. So the first thing you described about brain works like this and then neuroscience is like that, and you probably read some books, that's all correctly explained the classical paradigm in neuroscience. Right? That's how we explain the neuroscience when we don't have a better idea. But we also all know in neuroscience that it's not right, something's missing. So when you start explaining a new way, you have to basically abandon the old way. You mentioned the fact that there is recurrent connections. Of course, there's connections, like if I have these brain areas, this is projecting here and this one is projecting back, of course. Now, that's an anatomical fact, but what these projections do, that we don't know, right? So my claim is, if you go into this paper that I mentioned, there's more detail on it, but my claim is that this brain area helps that brain area, but this input, to change its own gates. This one helps this one to change its own gates, but the effect is seen only in the next iteration, only when the next round of the stimulus. So the stimulus goes here, connections go here, changes in gates, and then comes a new stimulus, and then only later you get the effect, only in the second round. If you want to see more details, please look at the paper.
With a pleasure. Yeah.
But now, which phenomena in neuroscience I'm going to explain? All of them. I try to get as broad coverage as possible, not just a few.
Okay.
Thank you.
That's first, second question, and then the third one.
So I have an operational question. What would be the criterion of success for this approach to work? Something like the Turing test for AGI. So when would you know that what you are putting forward is working as you intended to?
Maybe the robot from the beginning. If you would achieve such a robot that is able to do such tasks, learn such tasks, perform tasks, be sufficiently flexible, such that maybe not in the first iteration, not at the level of human intelligence, but at the level of cat intelligence, let's say. So that it actually avoids obstacles and does the job kind of in a fluid, flexible way, how you would expect it from a biological system. It would look like it's biological and it's really good where animals are good, and it's also bad where animals are bad. Right? So I think this would be something what I would be looking for. Right? I hope this does make some sense, because you're looking at me so as if it's not making sense.
Because that's hard. What you are saying is hard. You need, an entire manufacturing process to produce a robot, to do all the mechanical stuff. So
mechanical stuff, yeah.
Thought about something, something logical, like the Turing test, for instance, or some standard.
Okay, but I see where you're going. So the answer to this is, it's a different. So what this approach is saying is that we have to follow the evolution. And the evolution has first developed, bacteria, then plants, then simple animals, and only at the very end, a little addition to make human intelligence. Now, what we are doing with all the classical AI approaches, we're trying to skip this whole evolution process, just go to the top algorithm. What this is saying, no, you can't. If you want to get a human level intelligence, you have to go through these steps. So there's no really a point where you could do something similar to Turing test at the top, before you've done all this before. But when I'm here doing this, I will already know that it's working well, because it's working as intended. And then adding, only later would come the Turing test, the language, say, for example. Like animals have very little language, we humans excel at language. This would be the last thing to do, not the first thing. And the first thing would be simple reflexes, simple actions, just moving around, walking, doing something, but in a way how biological systems would do that. With short learning, small data, surviving, being able to survive. Something like that.
Okay, thanks.
Okay, we have an additional question in the girl in the back. Please just introduce your name and so we can be a little bit more personal.
Hello. It might be just a too simple question, but if I'm getting it right, you're just trying to add another, let's say, dimension of time to your classification model, let's say. Like we have for time series analysis, we have a time concept, and also a bit earlier today we saw an approach when for classification and object detection, some company used frames from video in representation as RGB models, like they send a frame from last second, from current second, and from the another second. So it gave the model some concept of time. So here it feels like it's something similar, like this concept of memory and time. Sorry.
Yeah, I agree that this is similar, but it's not just the time. There is an important time component. These gates have to last longer. If they don't last longer, there would be no effect that I'm promised at this point. I'm just only promising them. They need to last longer, right? But it's not the same precision of information that you would normally provide in such types of models, at least as far as I'm familiar with them. It's more like some sort of general rule, a little more general level of rule, something that applies, some rule that applies over a longer period of time. Right? So this is tightly related to situation. Let's say when I enter a room, or any of us enters a room, we enter a new situation. And a room requires certain type of actions, certain type of expectations, narrows down to something. And these gates can prepare your body, your network for this space that you have entered. But the idea is that this is going to last for a while. You're not going to just randomly jump to another room and then to space and then to forest. You're going to stay in this room. And that's how the body works. And it actually narrows down your network from all of the knowledge you have. Like deep learning network would have all the knowledge at all time activated. But here, as we go through the space, through the world, we basically activate the part that we know about this. So if I'm in a room, then I don't need a part of a network that works on the street, or that works on the forest, or that works when I'm skiing, or that works when I'm playing basketball. I just need a room knowledge. What I'm looking for, just to be able to walk from there to there, like avoid basic obstacles, whatever happens. So it's very much situational related. It's the presumption for this whole thing to work is that the world in which you live has situations. It doesn't change randomly. Classical deep learning network doesn't care about random. So you could just give it random tasks in any order, it's happy. It's just going to do equally well as if you just put things in order. For humans, you need things in order. You cannot just jump from one topic to another. It's really hard. We actually need time to rewire this whole thing. We actually need time to rewire it. Oh, now I remember some facts about this or something you didn't think about a long time. That's this process going on, right? So it requires situations, and luckily our world is built out of situations. Right? And also the home in which a robot needs to clean is built out of situations. When it's in a living room, then it's a living room. When it's vacuuming, it's vacuuming. It's not doing dishes. Later when it's doing dishes, it can only use the dishes doing network. And the vacuum network can be shut off with the gates. Hope this makes sense.
Okay.
Yes, thank you very much.
I have one last question, maybe a remark I didn't know because my brain just thinking to maximum like now after not sleeping for 3 days. But basically what you're explaining right now, I don't know if you had a chance to talk with somebody who has at least 2 or 3 PhD in physics. Basically what you're explaining is quantum teleportation of information, because basically how does electron work actually? It can choose to go back in time. Believe me, this is somebody who's done physics can explain also very, very good. You can choose back in time to go back in time and to choose a different path, because you know what is the optimal way. Basically what you're describing is the gate when they are activating or not activating is like energy barrier. So basically why does energy barrier exist? One of the theory is to make sufficient system. So it's classical system is saying that the energy is not there, so the electron cannot go to the other level. There is also like one part of the thinking that electron is not having enough energy because in the future they will show that that part will not be solvent one, so it's not using the energy. So basically what you're explaining, I don't know if you try to create gates with quantum computing, for example, because it could represent much closer what you're expecting. This is something, I think, subatomic things like what you're just describing to me, and this is something that I learned in high school, in mathematics high school gymnasium in Serbia. But basically this is one-on-one, like how did that function, like principles. And I think that if you try to just reach out to maybe somebody who has much better knowledge than me, understanding, this can be solved very fast, because that's how the nature works in the end. Like, it's not only about mathematics. People do tend to make a mistake about it, only thinking mathematics. Mathematics can be represented in different systems, but all of that system need to coexist in the physical world, and it has a limitation. It cannot be unlimited. And being said that, then you already has like equation has an end knowledge. And believe it or not, in the mathematics there's like 2D systems, and basically there's only one different thing, and it's very philosophical thing in math. does electron has free will? Not we. Who is the variable of the free will? If it's electron, you can choose. That's totally complete story. Like different aspects. I don't know if you talk about this kind of thing, this kind of approach, but this is like basically, I don't know.
I have to admit I don't know much about it.
Really?
So for me this is new. Of course I know basics, but I don't know much about this electron visiting past or knowing the future.
Basically, yeah, because you have to when you watch electron, you're not watching like this. It's totally differently. There's something that is physics are not explainable still that you don't understand.
This is new for me. Okay. I don't know. I should maybe learn, discuss, and ask. I'll ask my younger brother. He's a physicist.
Believe me, he will.
Yeah. Thanks.
Okay. So, do you have an additional question, or this is like the end? Okay. I would like to say thank you to Danko. This was an excellent. We had like 20 minutes, so let's big round of applause.